We're learning about Leslie matrices, and this is the first of two videos. We are going to introduce the idea of Leslie matrices, what they're used for, and some essential calculations to do with them, and reflect on the role of technology. So Leslie matrices came about in the 20th century from a mathematician called Harold Leslie. Harold Leslie worked at Oxford, I understand. So basically his model uses matrices, and it's for discrete population modeling over time, and a few assumptions are made, reasonable assumptions in the model, which we'll talk about. So it considers a biological term called fecundity, and basically that's to do with fertility. It's not exactly the same thing, I'm told. Now, I'm not a biologist, but it's not exactly the same as fertility, but it's a similar word. So it has a similar meaning, and the capacity to produce offspring. So we'll note that there. It's common practice in the model to consider only female offspring born to mothers, to female parents. Reason why is that paternity, fathers in the wild, is a bit of a problematic issue. In terms of tracking things and getting some primary data, some reliable data in field studies, it is possible to track the numbers of female offspring as a ratio of female parents because of the role in nature that mothers have. So maternity is easy to track, paternity is problematic, and so in Leslie matrix models we consider female offspring and female parents only in general. Now, it can be shown often in a lot of populations, 50% of the population are female. So if we want to get the entire population, we can simply multiply by 2. The modelling still works even if the females don't make up 50%, as long as they make up some recognisable fixed proportion of the population. We can then use Leslie matrices. So it's often 50%, not always. It works. The modelling works either way. Thus, we make the reasonable assumption the rates and the population changes in females at different age groups is also the same sort of population proportions and changes that are made with male, and therefore we can come to conclusions about the entire population. So we'll get that down. Okay. The mathematical calculations we will do with Leslie matrix models tend to be tech active, so you're usually going to use your graphics calculator or a spreadsheet depending on the context. Usually we need to justify by writing the matrix formulas down, the matrix algebra, and then we can crunch it with technology because it involves raising matrices to powers and multiplication of large matrices. Now what the model does is it divides, now this could be animals, it could be humans. We divide the population up into naturally recognizable age groups. For humans you could do it in decades, so the first 10 years, the second 10 years, and so on, up to perhaps something like 100 or 110. You can see just the top of a table just below here, and it's got a very different one. That's obviously not a human one. That's basically a couple of years per age group sort of spread, and that might be for a small animal. Okay, so like a possum or something like that. Whereas typically they don't live beyond 5 years. Okay, so it depends on the creature. For an insect, it'd be smaller again, wouldn't it? Each of these age groups are treated as discrete entities, and notice the age groups are all of the same duration. Now some important symbology and some terms. So we talk about the survival rate, and that has a capital S as its symbol. So for age group N, survival rate would have the symbol S sub N. And by the way, survival rate is 1 minus the death rate. So if by chance you're given data about the death rate, it's pretty much just the complement. So 1 minus death rate will give you the survival rate. Need to use survival rate. So survival of age group N, any of them, is always a value between 0 and 1. So 0 meaning none of that age group survive into the next time period. So example would be beyond this one, if you tried to set up a next age group, the survival would be 0 for here, for those people or those animals. Okay, so 0 means no survivors and 1 means 100% survival. We don't ever see it hit 1 really. We see it hit 0 when we're modeling the last group. We'll show this with some examples in just a moment. So the survival for the last group is 0. Next important thing we need is the birth rate, okay, which is B sub n, and B sub n is the average number of female offspring born for a mother in age group N. So basically it's the rate of offspring production for a mother in a certain age group, which we call N. Okay, so females, the rate of female offspring produced per female adult who is the mother. So typically S sub n and B sub n will be values, basically decimal values. In other words, I don't mean between 0 and 1 either. A survival rate is, but the birth rate, of course, can be greater than 1. Alright, it could be values like 2.7 or 1.8. Okay, it can also be down to 0 as well. We know a lot of species have multiple offspring. Okay, so that number for birth rate is not fixed to 1, unlike the survival rate. Let's generalize the matrix by first looking at some examples. So let's say we have a creature here, like it could be like a possum, like, so a smallish creature, and you can see we've got some data. Now this data may be primary data. Okay, so we need some data in the beginning, primary or secondary data. So primary is stuff that you might be part of a team and collected this directly from a field study, or it might be secondary data. You're using some published credible data. So it could be like a field study or some other validated research. So you need to start with some data, and the initial values come from that data, from the field. So this one is merely just showing that the female population is pretty justifiably, from tagging, the female population is pretty much a half. You can see row 2 population versus female, and it's pretty darn close to 50-50, so that's a reasonable assumption there. We also know that through tagging and observation, we have some data about the breeding rates for these naturally occurring age groups, and so you can see the breeding rate for the juveniles is 0. They're too young to breed, but once they get into the 1 to 2, so with the breeding rate, we can see there that the number can go past 1. With the survival rate, we can see that the creatures in their prime have the highest survival rate. It's a little bit lower at the bottom end, because sometimes babies can be eaten by predators, or they might die because of extremes in temperature and so on. The oldest creatures, because these only live to 5, have a survival rate of 0, so they don't go into, there is no next age category in the model for them. Now we can see that we could, by using these 3 tables, we could just use common sense and some direct calculations. If we use the female population in the first table, the breeding rate in the second, and survival rate in the third, we could just do some common sense calculations, okay, and get these numbers for the age-specific female population 1 year after this initial data. Okay, so remember, the natural progression is year by year. Okay, so these ones are in their first year. Okay, so if we did that, well, we would do the following. We'd look at, okay, in the next year we have 0 times 194, so that was that original 194 in that youngest age group. and they create no babies. So their contribution is 0 times 194, which is 0. The next group contributes that much to the next year, plus that group, plus that group's contribution, plus that group's contribution. And that's what they would add to next year. But that's not the only way we can have possums the next year. It's not just the babies, it's the older ones too. So it's the ones that survive into the next year, like most of them do. We see that here in the next row. We see that in the 0.6 times 194, because that's the survival rate of the previous year's youngest possums, and there was 194 of them up there, and you can see that that also makes a contribution. Alright, and then the group above survival rate, the survivors from the group above that and the survivors from the group above that. Notice how it stops there and it doesn't consider this 4 to 5 year old group, because they have a survival rate of 0, so there'd be no contribution. So we don't bother even calculating that one. And we get those a year later. So you can see that we have a change in the population. We had 194, 82, 55, 22 and 6. And now we've got a different population. We've got 227, 116, we've got 66, 44 and 9. So we have an increase there. Notice how it's rounded because these are discrete entities. So you might get decimals, but you have to round them to the nearest whole number. But of course we know a lot about matrices, and we could have actually done the whole thing using matrices. So this is where the idea of the Leslie matrix comes from. So we don't need to go through that clunky process, especially if we had a bigger set and bigger model, and we had more age groups, and we wanted to do it for many years. That would be a bit tedious. So let's use some technology and some matrices, and basically we could get the same by multiplying these two matrices together. Alright, and this one on the left, this big square one, is L, and L is the Leslie matrix. And this one here is the population vector, the initial population vector in its age categories. Alright, and that there is the result. So let's have a look in general. This is a Leslie matrix here. We call it capital L. So for a given model, the Leslie matrix is fixed. If we refine the model, we may make adjustments to the parameters if needed, and that would then be a different model. So importantly, we always put the birth rates across the top row from first to the last, where n is the last one. Now on this diagonal, it is not the leading diagonal. It's starting at position row 2 column 1. This element here is the survival rate of the first group, and it goes down a diagonal formation, and it ends not in the NN, but we are in row n, column n minus 1, and the last survival rate there for the second last group goes there. Alright, we saw that makes sense, because remember when we saw back here, that 0.4 was for the second last group, because the final group had a survival rate of 0, so they didn't form part of the calculation, and thus they don't form part of the Leslie matrix. So what we just did essentially in matrix form was this calculation. So remember, matrix multiplication needs to be conformable and in the correct order, so it has to be L times X. And by the way, instead of the symbol X, a lot of books write P for that column vector, that population vector, P for population. So you'll often see P instead of X. It's just a symbol. So it might be LP naught. So remember, the 0 and the 1 are a subscript, so that's basically saying Leslie matrix multiplied by the initial population vector gives you the age-specific population one cycle later, if that's 1 year or one decade, or if it's insects, it might be a quarter of a year later. So that'll give you the population one cycle later. Okay, in this case 1 year. Okay, and we would get, if we repeated that then, that process to get x2, we've got L times x1. Alright, and if you've got a minute, you might want to pause the video and see if you can enter that in. Enter those in, and if you do it twice, you get x sub 2, and you'll get that one there. You could possibly spend a minute verifying that with your graphics calculator, and you can just keep repeating it. So if you went ahead and redid the process and edited it, you'd get x3 and eventually x5. So that's after 5 years that for that population, you get that female breakdown for each age category there. So there'll be 661 youngest females and 35 of the oldest females by that point in time. Now, if you're going to go up to 10, that would be a lot of calculations. You might want to go straight to 10, and I'm going to show you how to do that, find a way of doing that. Okay, so more about that in a minute, because you can probably gather that's a bit clunky going year 1 to year 2 to year 3 to year 10 and so on. So I'm going to show you a quicker way. Just a little note here, in cases where the total population is required and where females are known to make up 50% of the population, we times all of those results, like this one here for example, by 2, and then add them together. And for x sub 10 we would get 9,441 females times 2 give you total. So without timesing by 2 we just get the females, but by timesing by 2 we get the total population of males and females based on our assumptions in the model. But using matrices, a quicker way is to actually multiply your column vector by a row vector of all 2's, and that will total and double, and you'll get the same thing done very efficiently. So I would recommend that there. Okay, so many tasks in books only want you to find the female population anyway. So read the question: does it want you to find the total, or does it want you to find only the females? And if you only had to find the females, you wouldn't need to multiply it by 2, and you wouldn't need that matrix. So it depends what the question's asking.